Hello and welcome to Lecture 2 of the Momentum Unit in Phys 1104. And we're not going to make it as far as momentum in this lecture. What we are going to do is use collisions between carts on a track to discover the idea of inertia. People often mix up inertia and momentum, but in fact they're very different ideas. So here's the first setup we're going to look at, and the blue cart is going to be moving to the right, and the red cart is going to be initially stationary, and I've set the track up with an ever so slight tip to it to compensate for friction, so that the carts will move at fairly nearly constant velocity. I didn't get it quite perfect, and you see that the one cart comes in, and it collides, and it appears to come to a full stop, and the other one moves away. Here is the x versus t graph for these two carts. You can see I've named them A and B, so x sub A is the x component of position of cart A. And you can also see from the graph that the one I've called cart A, which is in blue, is the one that was initially moving. You can also see when the interaction takes place. You can recognize the interaction because it's when the slopes of the two x versus t curves are changing. You can see it even more clearly in the x component of velocity versus time graph, because now whenever the velocity is changing, that means the two carts are interacting with each other. And so you can see fairly clearly the interaction lasts a little more than maybe 1/10 of a second. And the thing that's rather striking is the amount by which cart A slows down seems to be the same as the amount by which cart B speeds up. Or one way of looking at it is that the carts seem to have swapped velocities. Well, gee, what if this is a general rule? Why don't we make this a hypothesis that we can test? Sometimes when we have a hypothesis that we're really tentative about, we're not at all sure whether it's true, but we're just throwing it out there to see what happens. We'll call it a conjecture. Conjecture is a great word, so I'm going to use it and get fancy and say, here's Jeff's first conjecture of cart collisions. Whenever two carts collide, they will exchange velocities. We can test that. Well, we should vary some things, right? So we can vary the speeds of the carts, right? Here's another collision very similar to the first one, other than the fact that there's some friction messing things up. It sure looks like the carts exchanged velocities there. Well, what if we make both of the carts move? Well, here's the Vx versus t for that, and again, other than friction kind of getting in our way a little bit, it sure looks like the carts just exchanged velocities. Well, we can also look at what happens when the carts are moving in the same direction. Here's our Vx versus t for that, and that's looking pretty good. Again, it looks like the carts have just exchanged velocities. So far, this conjecture is holding up. But we've only been varying velocities. Is there something else we could vary? We've only been checking out identical carts. You might object, well, they're not quite identical, are they? After all, one's blue and one's red. And I'm sure you've encountered all sorts of situations where things of different colors behave totally differently, right? Well, in your own time, you can check out whether the color of the cart matters. But I think maybe something that might matter more would be the size of the cart. Up until now, we've worked entirely with identical carts, but now you see I've stacked two carts here. So we know there is twice as much matter in this, effectively, cart than this one. And so let's see what happens in the collision now. Do they still just exchange velocities? Well, clearly not. The red one has bounced back. The blue ones were certainly not going that way before the collision, so they have not exchanged velocities. If it wasn't clear to you just from watching the video of the collision that they didn't exchange velocities, maybe the Vx versus t graph makes it clearer. Look, the single cart, the red is showing the standard cart and the blue is calling the double cart. The standard cart was going along at around about 0.7 meters per second before the collision. Well, if they exchanged velocities, then the double cart would be going at 0.7 meters per second after, but it's clearly not. So we have to reject our hypothesis. These have not swapped velocities. That apparently, perhaps, only applies to identical carts. But if you examine this carefully, there's kind of an intriguing thing that perhaps might be a coincidence, but maybe not. Look, one of the carts is twice the size of the other. Well, one of them has a delta v of negative 0.9 meters per second, and the other has a delta v of 0.45 meters per second. That's a factor of 2. And it's the bigger one that has the smaller delta v. Could this be a coincidence? So I'm going to revise my hypothesis. Look, the single cart had twice the delta v that the double cart did. So I'm going to make that a new hypothesis, my second conjecture of cart collisions. When two carts collide and one is twice as big as the other, the ratio of their changes of velocity is 2, with the smaller one having the larger change in velocity. So we can test that hypothesis. Let's do the collision the other way around, with the double cart moving first and the single cart stationary. The hypothesis seems to be consistent with the result of the experiment. Here we are, and again, the blue is the double cart, and the orangey red is the single cart. And you can see that the single cart has a delta v twice as big as that of the double cart. In fact, they've happened to come out to the same numbers, not just the same ratio, but the same numbers. That's coincidence. I can do this experiment many more times with different velocities, but I'll always get that same 2-to-1 ratio. That's still not a very satisfactory hypothesis, though. It's too specialized. It only applies to one special case, when the carts have a size ratio of 2. But I think you can see the pattern. A size ratio of 2 leads to a ratio of change of velocity of 2, so it seems reasonable that a size ratio of n, so if one cart is n times as big as the other, then the ratio of their changes of velocity should also be n, with again the smaller one having the larger change in velocity. And of course we can check this, we can do lots more collisions, but I'll spare you having to watch all of those. I'll just give you one example. Here's a collision of a single cart with a triple cart, and you can see that the ratio of the delta v's is a ratio of 3. We can now propose a fundamental idea, because we already know that things keep going. In other words, in the absence of interactions, we've seen that objects move with constant velocity. So if you want to think of it that way, if you want to personify the objects, you could say that objects don't like changing their velocities. Well, when objects interact with each other, they do change their velocities, but big objects seem to be more resistant to having their velocities changed. And I'm putting big in quotes because there are several meanings we could use for big, and one of them is correct. So this idea is inertia. Inertia is a measure of how much an object resists changes to its velocity. And we know that big objects tend to have more inertia than small ones. This agrees more or less with the everyday meaning of inertia. It's not a commonly used word, but you'll hear people talk about how they had trouble getting up this morning because they had too much sleep inertia, or things like that. We use inertia to mean the tendency of something to resist change. This thing I'm calling inertia is something you've almost certainly already encountered, and you probably already call it mass. In fact, I usually already call it mass, and as we go on, we will use the symbol m to represent it, even though I'm going to keep calling it inertia. Well, why am I calling it inertia when you probably already know it as mass? Well, the reason is that the word inertia is more descriptive of the meaning of this quantity. This is something that quantifies how much an object resists having its velocity changed. And so the word inertia is meaningful. Just to illustrate, though, I need to clarify what I mean by big. suppose we have a plastic cart and a lead cart, and they're the same volume, and we let them interact with each other. Well, as I'm sure you can probably guess, the plastic cart is going to have a much larger delta V than the lead cart is. So what I mean by big is some measure of, well, really it's how many protons and neutrons and stuff like that are in it. And those are packed closer together in the lead than the plastic. But that's an atomic view or subatomic view of things that we can't really get into in this course. You already know the idea of density. And so you know that what is going to affect inertia is the volume of the object. So two objects made of the same stuff, but with different volumes, will have different inertias. But also, as the lead and plastic cart demonstrate, the type of material affects inertia. And that's it. That's all that affects inertia. The shape, the color, the surface texture, pretty much anything else you want to name has no effect on inertia. This process that we have here actually gives us a way of measuring inertia. So we can measure how many standard carts worth of inertia an object has by just doing the same experiment. We'll take a standard cart, collide it with an unknown cart, and look at the Vx versus t graph. And that allows us to get the two delta V's, the delta V for the standard cart, which I'll call delta V Sx, and the delta V for the unknown cart, delta V Ux. And then we've seen that if you think through the patterns we've been looking at, the ratio of the inertias is the reciprocal of the ratio of those delta V's. Plus this negative sign, right? Why the negative sign? Well, one of these delta V's is always in the opposite direction to the other. And so we need this delta sign because this ratio of delta V's will always be negative, but this ratio of inertias has to be positive. So that's what that negative is there for. Well, just solve that for the inertia of the unknown cart, and you now have that it is some multiple of our standard cart inertia. Well, all you have to do is replace your standard cart with a new standardized cart, which is 1 kilogram. That's its inertia, 1 kilogram, and you've suddenly found the inertia of the unknown cart in kilograms. So this is a way of measuring the inertia of an object. Now, I'm not going to claim it's a particularly efficient or easy way of measuring inertia, nor is it a particularly precise way, but it certainly would work.